You cannot pour sand into the ocean and expect it to stay in place. Yet Palm Jumeirah sits 3 miles offshore in the Persian Gulf, built from 94 million cubic meters of sand dredged from the seabed and shaped into a palm tree visible from space. The question isn't whether engineers could draw a palm in shallow water. It's whether they could stop the Gulf from erasing it. In 2001, Dubai announced a project that made coastal engineers around the world pause. The plan called for a man-made island larger than 800 football fields, housing 60,000 residents, built entirely from loose sediment in open water, exposed to tidal currents, storm surge, and ship traffic. No artificial island of this scale had been attempted in an active marine environment. The emirate had run out of beachfront property, and rather than building vertically or inland into the desert, developers proposed adding 78 kilometers of new coastline by terraforming the seafloor itself. The concept emerged from a basic economic calculation. Dubai's existing coastline could not accommodate the luxury development demand that drove the Emirates' tourism and real estate strategy. Extending the city horizontally into the Gulf offered more waterfront parcels than any conventional development could provide. The engineering constraint arrived immediately. Sand doesn't bond, it shifts with every wave and current. Dumping millions of tons of sediment offshore creates an underwater dune that marine forces will redistribute within weeks. The Palm's design required not just a shape, but a stable substrate capable of supporting high-rise towers, roads, utilities, and desalination plants on what had been open water 11 meters deep. Traditional land reclamation used rock or concrete caissons to contain fill material. At this scale, that approach would require quarrying half a mountain range. The project needed a method that could place sediment with architectural precision across an area of nearly 6 square kilometers, then prevent the Persian Gulf from dismantling that geometry the moment construction equipment left the site. Early feasibility studies examined the natural behavior of sediment in this specific section of the Gulf. Currents ran parallel to the coast at speeds between 0.3 and 0.8 meters per second during normal tidal cycles. Storm events could double that velocity. Any sand placed on the seabed without protection would migrate along the coast, redistributed by longshore drift until it either settled in deeper water or washed up on natural beaches kilometers away. Engineers calculated that an unprotected sand island would lose measurable volume within the first tidal cycle and be unrecognizable within a year. The design had to account for this continuous erosive pressure, not as an occasional threat, but as the permanent physical condition of building in open water. The solution began with a technique called rainbowing. A GPS-guided dredger positioned itself above predetermined coordinates and sprayed sand through the air in a controlled arc, allowing engineers to place sediment with accuracy measured in meters rather than hundreds of meters. The system used feedback from real-time sonar mapping. As the nozzle sprayed, computers compared the accumulating profile against the target elevation and adjusted flow rate and angle continuously. Over 18 months, the dredger deposited sand in layers, building the palm fronds and central trunk from the bottom up. The method allowed the island's shape to emerge gradually, each layer compacting under its own weight before the next arrived. But precision placement only addressed half the problem. The sand still had no structural integrity, and every tide pulled at the fresh slopes. Here's where the engineering decision changed. Instead of trying to stabilize 94 million cubic meters of sand, the team built a containment system around it. They constructed an 11-kilometer breakwater encircling the entire palm, using 5.5 million cubic meters of rock quarried in the UAE's northern mountains. Each breakwater stone weighed up to 1 ton. The structure didn't form a solid wall. Engineers left gaps to allow tidal exchange, preventing the lagoon from stagnating while reducing wave energy by approximately 80%. The breakwater sits on a geotextile membrane, itself anchored to the seabed, creating a zone where the sand island could settle without being stripped away by littoral drift. The membrane acted as a buffer between the rocky foundation and the soft seabed, distributing the immense weight and preventing the breakwater from punching through into the underlying sediment layers. But containment introduced a second problem. Cutting wave action by 80% also cut natural water circulation. Without tidal flushing, the lagoons inside the Palm would accumulate pollutants, algae, and thermally stratified dead zones. The design required artificial circulation, a series of submerged culverts that pull water from outside the breakwater and push it through the interior at a rate sufficient to replace the lagoon volume every 13 days. That system runs continuously. If it stops, water quality inside the Palm degrades within a week. The pumps and culverts represent an ongoing operational cost that will persist for as long as the island exists, a permanent infrastructure requirement that distinguishes this project from conventional coastal development. The island cannot passively exist. It must be actively maintained at the hydrological level. The project cost approximately $12 billion and required 6 years to complete the first phase. By 2006, residents began moving into properties on the fronds. The Palm became a proof of concept for 2 additional planned islands, Palm Jebel Ali and Palm Jumeirah, both larger in scope. But the 2008 financial crisis halted construction on the sister islands. Palm Jebel Ali remains partially built, and Palm Jumeirah exists only as a reshaped coastline with no vertical development. The economic viability of building cities from dredged sand became uncertain when demand collapsed. What had been framed as the first in a series of engineered archipelagos became instead a singular demonstration, its replication deferred indefinitely by market conditions rather than technical limitations. There's a geotechnical consequence that only became measurable after construction. The Palm is sinking, not catastrophically, but detectably. Satellite interferometry studies conducted between 2006 and 2020 measured subsidence rates between 2 and 5 millimeters per year across different sections of the island. That's within the range engineers predicted. Sand compresses under load as water is squeezed from the spaces between grains. The compaction is not uniform. Buildings on the outer fronds, where the sand layer is thinnest, are settling faster than structures near the trunk, where sediment depth exceeds 10 meters. Differential settlement creates stress on rigid infrastructure, roads, and pipe networks. Maintenance crews re-level roadways and adjust utility connections as the island continues to compress toward equilibrium, a process expected to continue for decades. This settling behavior means the island is not a static structure, but a dynamic one, gradually adjusting under its own weight and the weight of everything built upon it. The environmental cost remains disputed. Marine surveys documented loss of seagrass beds and coral communities in the dredging zones. Sediment plumes during construction reduced light penetration and smothered benthic habitats across an area larger than the island itself. The breakwater altered longshore sediment transport, causing erosion on adjacent natural beaches that required their own sand replenishment projects. Developers pointed to mitigation efforts, artificial reefs installed on the breakwater, water quality monitoring, and restrictions on dredging during coral spawning seasons. Independent assessments concluded that while some marine life colonized the new hard structures, the net biodiversity outcome was negative. The palm created habitat, but destroyed more than it replaced. The trade-off was explicit: new real estate in exchange for established marine ecosystems, a bargain that coastal environmental regulations in other jurisdictions would not have permitted. Today, Palm Jumeirah houses luxury hotels, residences, and a monorail connecting the outer crescent to the mainland. Occupancy rates fluctuate with Dubai's real estate cycles, but the island remains operational and occupied. It proved that large-scale marine land reclamation is technically feasible in the 21st century. The rainbowing technique, GPS-guided dredging, and rock breakwater containment have been adopted in land reclamation projects across Asia and the Middle East. The design became a template, not because it was cheap or sustainable, but because it worked within the constraints of available materials and existing marine construction technology. Projects in Singapore, China, and other Gulf states have adapted elements of the Palm's construction sequence, refining the method but not fundamentally changing the approach. The lesson isn't about ambition. It's about containment. You can reshape the seafloor if you accept that the ocean will test every boundary you build, and that holding sand in place costs more than putting it there. Palm Jumeirah didn't solve the problem of building on water. It demonstrated that the ocean can be temporarily constrained at sufficient scale and cost, and that the engineering challenge isn't the island itself, but the continuous systems required to keep it from behaving like sand. The real accomplishment was not architectural, it was hydrological, building a barrier strong enough to create a pocket of stillness in moving water, then engineering artificial circulation to prevent that stillness from becoming stagnation. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.